All right, open up your book to section 6-2. We're on page 284 in your book. Title of this section is The General Sinusoidal Graphs. And the objective is, given any one of these sets of information about a sinusoid, we want to be able to find the other two. So if we're given the equation, or the graph, or the information about that particular sinusoid, the amplitude, the period, or the frequency, phase displacement, and the sinusoidal axis. Given any one of these, we want to be able to find the other two. All right, so let's start with a definition, first of all, of what a sinusoid is. A sinusoid is defined as any translation or dilation of the parent function y equals cosine of theta or y equals sine of theta. So we've already looked at what the graphs of those functions look like when we first started working with sine and cosine in the previous chapter. We sketched at least one period of those. And now if I apply any translation or dilation, like we learned from chapter 1, to those functions, I end up with a sinusoid. And if you recall, in chapter 1, we looked at the general equation of a function that has had translations and dilations applied to it. And we wrote a kind of a long equation like this that involved A, B, C, and D. There is one slight difference here from how we write the general sinusoidal equation from what we saw in chapter 1, but you have two equations that look very similar, and basically we're replacing sine with cosine between the two is really the only difference that we see here. So you have y is equal to c plus a times the cosine of the quantity, b times theta minus d. And the other equation, y is equal to c plus a times the sine of the quantity, b times the quantity theta minus d. Again, that should look very similar to a nice little formula that we wrote out in chapter 1. One thing you'll notice that's a little bit different here is the horizontal dilation, that b value. But if we want to compare this with what we saw in chapter 1, in terms of your dilations, the a would be equal to your vertical dilation. In this case, since we're writing it as just b and not 1 over b like we did in chapter 1, it turns out that 1 over b is actually your horizontal dilation. And the c and the d, those are your translations. So c is your vertical translation, and d is your horizontal translation. All right, so the good news for us from the equation we learned back in chapter 1, this is the same equation basically, but instead of having this in terms of a function f, we're replacing that with sine and cosine. And there is that one little change there with the horizontal dilation. Instead of writing it as 1 over b, we write it as just b in this equation. So that means that the reciprocal of b that we've got in this equation here is actually the horizontal dilation factor. All right, so let's talk about what each of these represent. What we've written over there on the right there is definitely a way you can describe this in terms of dilations and translations, vertically and horizontally. But when we're dealing with a sinusoid, we have special names that we give to these. So not only is A referred to as a vertical dilation, it's in the case of a sinusoid, we call it the amplitude of that sinusoid. And actually, it's the absolute value of A. A could be positive or negative, and it's the absolute value of it that gives us the amplitude. The amplitude is always positive, in other words. When you look at the b value, the b value will tell you something about the period of this function. It turns out that the period of this function is equal to 360 divided by b, and actually it's the absolute value of b, because again, b could be negative in our equation, but the period is always positive. So it's 360 degrees divided by the absolute value of b. Or actually, if you wanted to write that another way, you could say that the absolute value of b is equal to 360 over the period. If you solve that for the absolute value of b, this is what we'll end up with. Same equation, just solve for a different unknown there. So it depends on what you know as to which one of these two you might want to use. But the period and b are related, but realize that the period is not equal to b. They're not equal to each other, but there is a relationship between the two. The next one is the C value. So the C value, again, instead of calling this a vertical translation like we did back in Chapter 1, on a sinusoid, we refer to this as the sinusoidal axis. And we call it the sinusoidal axis because of the fact that we'll see that our sinusoid oscillates back and forth around this value of C. It's kind of like a midline right through your sinusoid. So that's our C value. And C could be positive, negative, it could be 0, it could be anything. It's just the value of C is your sinusoidal axis. And the last one here is our phase displacement, D. Instead of calling it a horizontal translation here with a sinusoid, we call that the phase displacement. And that's our value D. And one last one that we should talk about here is the frequency. And it turns out that the frequency and the period are reciprocals of each other. They're inverses. The frequency is equal to 1 divided by your period, or that's another way of saying that your frequency is the absolute value of b divided by 360. Just taking what we have up from up above and reciprocating that, you can write that frequency is the absolute value of b over 360. Now, depends on the problem and depends on what you're modeling as to why you might choose one or the other, a period versus the frequency. If the period turns out to be really, really small, then the reciprocal of a small number is a big number. And so sometimes you'll see that written as a frequency instead, because that way it's a larger number that you're working with. But realize when we go to write the equation, it's not the frequency I need to know, it's the period that I need to know to figure out what that value of b is. So if you're given frequency, reciprocate it to get period, and then you can go from there to find your equation. So there's our values of A, B, C, and D, and what they represent in this general sinusoidal equation. All right, so let's take these two equations, and let's sketch ourselves a sinusoid here. That's what we've got, just a general sketch of some sinusoid. It's oscillating back and forth. This is what the cosine function would look like. I've got a couple of axes marked here. That's the darker lines that you see there, your x and y axes. And then I've also marked a couple of lines in here just to help us mark some key values, and in particular relate that to the general sinusoidal equation that we just saw. All right, so let's write down this general sinusoidal equation actually, first of all. We had y is equal to, and the first thing that shows up in that general sinusoidal equation is the value of c. Y is equal to c. So what exactly is c? Well, c is this line that goes right down the middle of our sinusoidal axis. So that's that horizontal line that goes right through the middle of it. For right now, that's going to be just some number, a constant, and so it will be a horizontal line. But you could modify that. It could have a variable in there, which means that your sinusoid would not oscillate around a horizontal line, but maybe in a line that has a slant to it. All right, so our equation is y is equal to c plus, I'm just going to do these in different colors here, c plus a. So the absolute value of a, remember, is your amplitude. And the absolute value of a will tell you how far it is from your sinusoidal axis to your upper bound, or from your sinusoidal axis to your lower bound. So if I were to measure this distance right here, that would be the absolute value of a. Or measure this distance from the sinusoidal axis to the lower bound, that's the absolute value of a. Both of those are the same. So in other words, I could write this as c plus the absolute value of a up here, or this could be c minus the absolute value of a down here. That's our upper and lower bound. All right, that's the first part of our equation here. We're doing cosine here, so I'll put in cosine now in my equation. And then the next thing that shows up in my equation there is this value of b. Again, I'm just trying to color code this here for us. So b is the next thing that shows up. So b is on our horizontal axis. b is related to your period, remember. So it turns out that if you take 360 divided by the absolute value of b, that tells you the distance from one point to the next corresponding point on that particular cycle there. So this distance right here is the period, and the period, remember, is equal to that 360 divided by the absolute value of b. Okay, so again, that distance is not equal to b. The distance is equal to the period, and the period is equal to 360 over the absolute value of b. So I can't necessarily sketch what exactly b on this graph, but I can show you how we can calculate it from this graph. All right, and then it was b times theta minus, and then the last value here for us to find or to understand is this value of d. Close off those parentheses there. All right, and so the value d is the phase displacement, and the phase displacement tells you the location of your high point for the cosine function. So d is this value right here, this x value right there, because I can see that the cosine function is hitting its high point. So that's my value of d. In some problems, you might know both of the high points. So if that's the case, then just realize that I've got d here on the left, and then this would be d plus my period, or that's d plus the 360 over the absolute value of b, is another way of thinking of that. If you want to think of those 2 points in terms of b and d, what are they equal to? That would be the way we'd represent those. Now the reason why d is the location of our high point, go back to the parent function, y equals the cosine of theta, and consider what's happening right at the x-axis there for the, right at the y-axis there for our cosine function. The cosine function is doing something like this, and in particular, right at x equals 0, that's where this function hits its high point. High point right there at x equals 0. So when I do a horizontal translation of this function, I'm basically moving that point, along with every other point, of course, but the easiest one to track is that one. I'm moving that point to someplace d. That's why d is the location of the high point, because of what happens on the parent function at x equals 0. All right, that right there is our cosine function. Let's compare that with our sine function. We write our sinusoid in terms of sine, what do we end up with? The good news for us is most of the things that we just wrote down apply to our sine function. But there is one key difference here for us to note. So again, let's write down our equation. Y is equal to, and again, I'm going to color code this as we go here. Our equation is y is equal to c. And again, the c is just the sinusoidal axis. It's the line that goes right down the middle of this. So that turns out to be this guy right here, that horizontal line. And it's y equals c plus, and then it's the amplitude, value a, or actually amplitude is the absolute value of that. But again, that vertical distance here between this high point and the sinusoidal axis, that is the absolute value of a, or between the sinusoidal axis and your lower bound, that is the absolute value of a. Started to write b. A. Or in other words, I could mark my high and my low points, my upper bounds and lower bounds, as c plus the absolute value of a. Or I can mark this as c minus the absolute value of a, just like we were able to do there with the cosine function. All right, so it's c plus a times the sine of, and then it's our b value. And b, again, is representing the period of our function, or it's, or I should say, related to the period of our function. So this horizontal distance right here is the period. And that's equal to 360 degrees divided by the absolute value of b. Again, I can't stress this enough that b is not the period. B is related to the period, though. You measure this distance, and then that distance is equal to 360 divided by your period. And then you can solve to find out what b must be equal to. And then finally, the last part of this is theta minus, and then it's d, theta minus d. D is our phase displacement. This is the difference between these two functions. The a and the b and the c, you'll notice, are exactly the same. We measured those all the same way. Although I guess the period we marked here as being the place where we cross the sinusoidal axis and we're increasing to measure that distance, but it wouldn't have mattered whether I measured from between those 2 points or any other 2 corresponding points. I'd get the same measurement there for the period. The d value is different, though. The d value is our phase displacement, and for the sine function, I have to be crossing the sinusoidal axis and increasing. And so this is the value of d that I'm looking for. Okay, notice that it's not this point right here, because that point right there, I'm crossing the sinusoidal axis, but I'm decreasing as I go through it. In other words, there's 2 possible things that you could look for, or 2 possible values that you could be considering here when you're looking for the value of d for sine. Got to make sure you get the right one. It's not just enough to say it's where you cross the sinusoidal axis. You also have to be increasing as you go through it. And of course, if you wanted to name this value over here, this would be d plus the 360 over the absolute value of b. All right, and again, if you want to see why exactly is that the value of d, we'll go back to your parent function, y equals the sine of theta, and sketch that graph. Sine is a function that does something like this. So notice what it's doing as it goes through the the y-axis there. As it crosses the y-axis, now we're crossing our sinusoidal axis. That's the halfway point of this function between its high and low points. That's at x equals 0. So just like we talked about with cosine, what we're actually doing is figuring out with that phase displacement, how far am I translating that point right there? So that's why I'm looking for that point here on my sketch. Got to cross the sinusoidal axis, and I got to be increasing. Or in other words, I got to cross the x-axis there on the parent function and be increasing. All right, a couple of graphical features here that we've talked about some of these features before in our previous chapters, but just to make sure we're clear on what these features are here on a sinusoid. The sinusoid is really nice because it kind of has these horizontal lines that split this up into kind of 2 different sections vertically in your range. And actually that kind of divides it nicely into our sections here where we have different concavity. It turns out that if you're above the sinusoidal axis, that your graph is concave down. That shape right there is concave down. Here we are concave down again. And if you're below the sinusoidal axis, you're concave up. So this is concave up right here. And the key points where we transition from one to the other are what we call points of inflection. So these values right in the middle here between these places where we're concave or up or concave down, those are called points of inflection because we're changing concavity. That's the term given to those particular points. Turns out, on a sinusoid, that's where you cross the sinusoidal axis. All right, but other functions have points of inflection, but they don't have a sinusoidal axis. So don't read too much into that definition here. On a sinusoid, it turns out the points of inflection are on the sinusoidal axis. But it's really, a point of inflection is where you change concavity from being concave up to concave down. The other term that we'll use here to describe this is this idea of upper bounds and lower bounds. Those are those terms that are written off to the right here. We've got an upper bound, that's the highest that our sinusoidal gets, and the lower bound is the lowest that our sinusoid gets. So those are the upper bounds and lower bounds. And the last thing is the critical points. When you look at a function, when you hit your high point, your upper bound, like we do at these two places, or I hit my lower bound, like I do there, we call those critical points. Okay? So critical points are where we hit the highs and the lows there. We'll learn a little bit more about critical points next year in calculus and talk a little bit more about those, but we should understand that those are what those points there are referred to as critical points of that function. All right, let's take a look at a couple of examples here. Let's start with the example 1 there on page 287. It says, suppose that a sinusoid has a period of 12 degrees per cycle. It has an amplitude of 7 units. It's got a phase displacement of -4. And with respect to the parent cosine function, that is critical, that if they're going to tell me phase displacement, which one of the functions are you talking about? Because for cosine, it's one thing. For sine, it's a different thing. Remember, that's the difference between the two graphs that we just looked at. That's the d value. And the sinusoidal axis is 5 units below the theta axis. And it says, without using your grapher, sketch the sinusoid and then find the equation of it. Okay, so let's kind of fill in the information that they've given to us, but let's sketch ourselves a general sketch of a sinusoid. It doesn't have to be exact here. Just give yourself a sketch to kind of get started with and fill in the key values here. In fact, the two lines that I drew here don't even have to be your x and y axes, so don't try to get those right in the right spot. But rather, those are just places that I'm going to mark some points that I need to know. So they tell you that it has a period of 12 degrees per cycle. So that's the distance between these high points then. So this distance right here is 12 degrees per cycle. The amplitude, they tell us, is 7 units. So if I draw in my upper bound, and I draw in my lower bound, and I draw in my sinusoidal axis that goes right down the middle of it, they're telling me that, I should have done that in a different color here. They're telling me that this distance right here is 7 units. Let me change the color of this here for us. This was 12 degrees. And then it says it has a phase displacement of a -4 degrees. So phase displacement, that's going to be the location of this high point for us, since we're doing this in relation to the cosine function. So that's at -4 degrees. And then finally it says it's got a sinusoidal axis of 5 units below the theta axis. So this is actually at a -5 is what they're telling us here. Okay? And basically the sketch helps us kind of see what's going on here, but realize with the information they gave us, we should be able to come up with the equation. But I like sketching this each time because that helps us come up with our equation every time. Oops, we're going to do this in terms of cosine. So let's write down our general equation here. C plus A times the cosine of B times theta minus D. And now let's fill in the A, B, C, and D here. C, again, is your sinusoidal axis. So they told us that was -5. A is the absolute value of A is our amplitude. They told you that was 7. Cosine of. Now, they told you the period, so they didn't tell us B in this problem, but I know that I can find the value of B by taking 360 divided by that period. In fact, I'm going to leave it in that form. 360 degrees divided by the 12 degrees. I like leaving it in that form because when you look at that, if the value of B is written as 360 divided by some number, then I can immediately look at that equation and tell you what the period is. It's the 12 degrees. If you simplify it, then you got to do a little bit of work to figure out, okay, what's the period of this function? So I'm going to leave it in that form, and I'd suggest you do the same. And then it's theta minus D. Your phase displacement is a -4 here. I'm going to go ahead and write it that way, but if you want to change that to addition, you can do so. There is our equation of this sinusoid. So now, let's grab our calculator and sketch this. All right, so with our calculator here, first of all, make sure that your calculator is in degree mode. I would assume that's the mode you're currently in. We will be doing some stuff with radian, but not quite yet. And then let's go to our y equals menu, and we're just going to punch this equation in here. It was -5 plus 7 times the cosine of I'm going to leave that as 360 divided by 12. You can simplify that, of course, but I like leaving it in that form. And then it's x minus a negative 4. I'm going to go ahead and just write that as x plus 4 here. But if you want to write it as x minus a negative 4, certainly you can do that. All right, now I'm going to use the window that they basically gave us, or I should say the window we sketched, to help us get a nice window to show this in. If you go to your window, on our sketch there, horizontally, we marked where the phase displacement was, which was at negative 4. And the period was 12. So 12 units to the right of that would be at positive 8. So I'm just going to look at just one period of this. In fact, I'm going to try to fill my screen with just one full period of this function. And then the y values, the lower bound there, well, it was the sinusoidal axis was at negative 5. I guess we didn't mark those on our graph. We probably should have. But the amplitude was 7. So 7 units below negative 5 would be a negative 12. And 7 units above negative 5 would be a positive 2 there. Again, probably that would be a good thing to have on your sketch there. But if we graph this now, we should see that our sketch completely fills the window, which is what I'm seeing here. I see one full period of this, goes all the way from the bottom to the top of my screen there. That's exactly what I'm looking for. So my sketch seems to be right there. I'm going to go ahead and grab a copy of that. And we'll just paste it in here. All right, and that's what they want us to do for example number 1. Let's take a look at example number 2 on page 288. Example number 2 says, for the sinusoid that they've given us here, give the period, the frequency, the amplitude, the phase displacement, and the sinusoidal axis location, and then write the equation of the sinusoid and check that your equation is correct by plotting that on your calculator. Okay, so we'll do that. But let's go ahead and find the values that they're asking us for here. I guess the first thing that I want to do is actually to find the values of A, B, C, and D, and then we'll actually figure out what our period and frequency and all that stuff is here. So let's first find our value for A. A is the amplitude of this. And the amplitude, if you just take the distance between your upper bound and lower bound, that's this distance right here. If you just take half of that, that'll tell you the amplitude of this. So we'll calculate that. That's 56 minus a negative 38. And we want half of that, so divide that by 2. So 56 and 38 is what? 80 and 14, 90, 94. Half of 94 is what? 47 is the amplitude. So we just found out this distance right here is 47. All right, the next thing we need to know is our value of C. I guess I'm going to find C next. I'm going to do my vertical translation and dilation first. So C is the sinusoidal axis. And so if I just find the midpoint between these two, that is this distance right here, if I add it up and divide between those two, that'll tell me my value of C right here. So if I take 56 plus a negative 38 and divide that by 2, again, I'm just finding the average of those two, add them up and divide by 2. What does that give me? If it was 36, that'd be 20, so that's 18. Half of 18 is 9, is what we should have there. So it turns out that our value here, C, is equal to 9. Maybe I'll just replace the C here with 9. That's what that calculation does for us. And now, let's go ahead and find out our value for B. B, remember, is equal to or related to the period. So B is equal to 360 divided by your period. So the period is the distance between these two right here. This is our period. So that's 23 minus 3 will give me the period. In fact, I'll write it that way. If we take 360 degrees, take 360 degrees and we divide it by the 23 degrees minus the 3 degrees. That's the period of that. So that's over 20. So that's 360 over 20. And I'm going to leave it in that form as our b value. And then finally, for the value of d, d is just the location of your high point for cosine here. So this high point right here occurs right at a value of 3. So d is equal to 3. Oops. We have d is equal to, I'm just trying to color code this for us so that we can see these values clearly. D is equal to 3 degrees. All right. Now let's go ahead and answer the question that they asked us here. They asked us for, they didn't ask us for A, B, C, and D yet. They did ask us to write the equation, so we're going to need that. But they asked us to list what the period and the frequency and so forth are. So let's list those. So we have a period that we found was equal to 23 minus 3 degrees, which is 20 degrees. The frequency, remember the frequency is equal to the reciprocal of your period. So once you find the period, you just take 1 divided by that. That's 1 over 20. They asked you for the phase displacement. So the phase displacement, that's our value of d. That was 3 degrees. They also asked you for the sinusoidal axis. That's that line that goes right through the middle, which we found was 9. And I skipped over the amplitude there. They asked us for the amplitude. I missed that in going through that list, so let's write that down. Amplitude, again, we've calculated that. That's the absolute value of A, and we found out that A was 47. So there we go. There is our 5 values they've asked us for. We've already figured out what A, B, C, and D are, so let's just write our general equation then. Either from all of this or the work that we did up above. We have y is equal to, our sinusoidal axis is 9, our amplitude is 47, cosine of, I like writing this as 360 divided by the period, which we said was 20 degrees, times theta minus your phase displacement, which was 3 degrees. And I'll let you, they say check that by plotting that. I'll let you grab your calculator and you can plug it in and make sure that, in fact, that is the right sketch there. But that is our equation of this sinusoid. All right, and that's the end of this first half of section 6-2.